Hello. I've got here some solved problems on the first four lectures about gears. So I just thought to try to solve some problems to cover the concepts uh, in the lectures. So we have the first problem here. It says find the angular velocity of gear 8. So here is gear number 8. So the velocity of this gear is required. If the angular velocity of gear 2 is 800 rpm in the direction shown. So we have been given here the velocity of this gear, or the angular velocity of this gear number 2. It's 800 rpm and it's in the counterclockwise direction. As you see here, we have a kind of complicated gearbox or gear train, but all the number of teeth are given for all the gears, and the speed or the angular speed of the first gear is given, and it is required to find the angular speed and direction of the last gear number 8. Gear number 2 here has 18 teeth. Gear number 3 and number 4, they are on the same shaft. Gear number 3 has 44 teeth. Gear number 4 has 15 teeth. Gear number 5 and gear number 6, they are on the same shaft. The number of teeth for gear 5 is 33. The number of teeth for gear 6 is 18. Gear number 7 has 25 teeth, and gear number 8 has 48 teeth. You see here that gear number 2 is engaged with gear number 3. It's external engagement. So at this point, so gear number 2 is the driver, gear number 3 is the driven. Because gear number 3 and gear number 4, they are on the same shaft, so they do have the same speed. But here, gear number 4 is engaged with gear number 5, external engagement. So they are externally engaged here at this point. Then gear number 5 and gear number 6, they are on the same shaft, so they do have the same speed. And so then gear number 6 is engaged with gear number 7 at this point. So gear number 6 is the driver for gear number 7 at this point. And then gear number 7 drives gear number 8. So they are externally engaged at this point. So what's required is how to find, using this data, how to find the speed, the angular speed of gear number 8 and its direction. We'll go back to the definition of the train value. So the train value E is equal to the product of the driving tooth numbers divided by the product of all the driven tooth numbers. So we need to identify the driver gears and the driven gears, and we need also to find or to recognize the number of teeth for each one. After we find the train value E, so we can use this equation that N sub L, which is the speed of the last gear, which is in this case gear number 8, is equal to E, which is the train value, multiplied by the speed of the first gear, which is in this case gear number 2. So the key here is to find E. If we find E, so we can, using this relationship, we can find the speed of gear number 8. So the train value is given as, we'll just look at our train here, or gear train, and then recognize which one is the driver, which one is the driven. And we'll take them stage by stage. So for example, here we see that gear 2 and gear 3, they are meshed at this point. So in this case, gear number 2 is the driver, gear number 3 is the driven. So we consider this as our first stage. So it's N2 divided by N3. N2 is the number of teeth of the driver gear, which is number 2 in this case. N3 is the number of teeth for the driven gear, which is N3. So moving to the next stage, so gear number 3 and gear number 4 here, they are on the same shafts. They do have the same speed. And then gear number 4 and gear number 5, they are engaged at this point. So gear number 4 is the driver, gear number 5 is the driven. So N4 divided by N5, N4 is the number, gear number 4 is the driver, gear number 5 is the driven. I'm just putting negative here because they are externally engaged. If they are externally engaged, we put like negative sign for this ratio. If they are internally engaged, so we put the positive sign. So this is negative, this is negative. All of them are externally engaged. That's why we have negative here for all the stages. So the next stage is that between 6 and 7. So 6 is the driver, 7 is the driven. So N6 divided by N7. And then the last stage is 7 and 8. So N7 is the driver and 8 is the driven. And as we've agreed, all of them have the negative sign. So if you multiply negative by negative by negative by negative, you will get positive. So the number of teeth for gear number 2 is 18, and the number of teeth for gear 3 is 45. So 18 divided by 45 for the first stage. 15 by 33 between 4 and 5. So 4 has 15 teeth and 5 has got 33. So it's 15 divided by 33. Gear number 6 has got 18, and gear number 7 has got 25 teeth. Gear number 7 has got 25 again, and gear number 8 has got 48. So if we multiply all these together, you are getting 0.0697. This is your train value. So going back to the equation, the speed of the last gear, which is in this case, it's gear number 8, is equal to the train value, which is 0.0697, multiplied by the speed of the first gear, which is 800, gear number 2. So we're getting here 52.79 RPM. Because it's positive, so it's in the counterclockwise direction. If it was negative, so we would have said that it's in the clockwise direction. But I've got a figure here as well to show this. So if gear number 2 rotates in the counterclockwise direction, this was given. So it is externally engaged with gear number 3. So gear number 3 rotates in the opposite direction. So if this one rotates in the counterclockwise direction, this one will rotate in the clockwise direction. 3 and 4, they do have the same speed, the same direction. So 3 and 4, they rotate in the clockwise direction. So if gear number 4 rotates in the clockwise direction, so gear number 5 rotates in the counterclockwise direction. 5 and 6, they have the same direction and speed. And you see here that gear number 6 rotates in the counterclockwise direction, so gear number 7 will rotate in the clockwise direction. 7 and 8, they are externally engaged. The direction of their speeds is different, is opposite to one another. So gear number 7 rotates in the clockwise direction, so gear number 8 will rotate in the counterclockwise direction. So this is how we verify that the gear number 8 will rotate in the counterclockwise direction. So the problem number 2 here, we have 2 parallel shafts. As you see here, we have an input shaft, we have an output shaft. These 2 shafts are parallel, and they are 600 millimeter apart. It says about here, so approximately 600. It's not exactly 600 millimeter. So see here is approximately 600 millimeter, the center distance. So about 600 millimeter apart are to be connected by spare gear. So we need to design a spare gear train here between these 2 shafts to transfer the power from the input shaft to the output shaft. One shaft is to run at 360 RPM. So if the shaft here, the input shaft rotates with N1, that is 360 RPM, and the second shaft rotates at 120 RPM. So design the gears. Design the gears meaning that find the diameter of the gear, the pitch circle diameter of the gear, find the number of teeth of the gear. If the circular pitch is to be 25 millimeters, so the circular pitch here is given as 25. So the facts that are given here are the RPM of the first shaft. This has to be exact. The RPM of the second shaft, which is 120 RPM, this has to be exact as well. And the ratio between them, because if you get the gear ratio, the N input or the N1 divided by the N output or N2, you will get here the gear ratio as 3. So this is a fact as well. This has to be exact. So we need to keep the speed ratio to 3. And the pitch circle has to be 25 as well. This is fixed, so we cannot change this 25 millimeter. We cannot change the 120. We cannot change the 360. For the center distance, it's approximately 600, so we can just get it like a little bit higher, a little bit lower than the 600. So what is given here is the center distance is 600 millimeter, the speed of the first shaft and the first gear consequently is 360 RPM. The speed of the output shaft and the speed of the output gear is 120 RPM, and the circular pitch is equal to 25 millimeter. And the circular pitch is the same for gear 1 and gear 2. So if we assume that d sub 1 is the pitch circle diameter of gear 1 and d sub 2 is the pitch circle diameter of gear 2. So coming back to the gear ratio definition. So the gear ratio definition, we call it M sub G. Gear ratio is equal to the speed of the first shaft divided by the speed of the second shaft. And you see here that N1 is higher than N2. So when we relate this to the diameters, we need to use the higher diameter on the top and the lower diameter on the bottom, just to be consistent with this one. So N1 is high, D1 is large, N2 is small, so D1 is small. So the mg, which is the speed ratio or the gear ratio, is equal to 360, which is given, divided by 120 equals d2 divided by d1 is equal to 3. When you divide these two, it gives you 3. So if we simplify this part, so d2 divided by d1 is equal to 3, it will give us d2, which is the diameter of the second gear or the pitch circle diameter of the second gear, is equal to 3 times the pitch circle diameter of the first gear. This is our first equation. So in order to get D2 and D1, we need one more equation. So we've been given also the center distance between the two shafts, which is about 600 millimeters. So we use it as 600 millimeter for now. So if we say that C is 600 millimeter is equal to D1 plus D2 divided by 2. So if we multiply the left and the right hand side by 2, we are getting here D1 plus D2 is equal to 1200. And this is our second equation. So now we have two equations and two unknowns, so we can solve them together to get the diameter D1 and D2. So if we substitute the first equation into the second equation, we have here D1, and we know that D2 is 3 times D1, so we just substitute here 3D1 is equal to 1200. So on the left-hand side, we have 4D1 is equal to 1200, and consequently D1 is 300 millimeter and D2 is 900 millimeter. So we've got now the pitch circle diameter for D1 and D2, so we need to get the number of teeth. Now, how to find the number of teeth on gear 1 and 2? We've been given the circular pitch. Circular pitch is equal to pi multiplied by d, the pitch circle diameter, divided by the number of teeth, capital N. So capital N is the number of teeth. So for gear 1, we know that P is given as 25. So P is equal to pi multiplied by D1, the pitch circle diameter of the first gear, divided by the number of teeth of the first gear. So we can apply this equation for first gear and for second gear. So in this case, if we simplify this equation to find N1, so N1 here is equal to pi D1 divided by P. D1, we just calculated D1, it's 300, and then P is given as 25. So we are getting here 37.7. We cannot take this number as the number of teeth. It has to be integer number. So either we take it at 37 or 38, but because it's 37.7 here, so it's more close to 38. So we consider this as 38. Then we can use the same equation. The circular pitch is equal to pi d2 divided by n2, where n2 is equal to pi d2 divided by p. P is given 25. D2, it was calculated as 900, so we're getting here 113.1. Though we cannot just take this number and assume that it has to be integer, we can take it as 113 or 114 straight away. We just need to make sure that the speed ratio is 3. And we understand that the speed ratio is equal to the number of teeth, the higher number of teeth divided by the lower number of teeth. And in this case, it's n2 divided by n1. So n2 divided by n1 has to be 3. We've already chosen this to be 38. So if we've chosen this to be 38, so this number n2 has to be found using the speed ratio. So n2 divided by n1 is equal to 3. If n1 is equal to 38, so here in this case, n2 is going to be 114. So this number is a guide for us now. It's just, it is used as a guide because, for example, someone could have chosen n2 to be 113. In this case, if you divide 113 divided by 38, it doesn't give you 3. So in order to have the speed ratio exactly as 3, so you need to get the n2 from here. And then this equation can be used as just a verification. So it's very near from here. So we are safe now. So in this case, if I go back here, so I've just got this number at 38. It was 37.7, and I've got it at 38. I rounded this number up to an integer number of 38. If you look at the left-hand side here, you will find that P, we cannot play with P. P has to be 25, exactly 25. We cannot change this at all. But if you are playing with this number, something has to change here just to balance this change. So we have here rounded up this number to 38. We cannot change P, so we must change the diameter in order to make this as 38. So we need to find the diameter again, the exact D1 for now. And then we need to do the same here because the N2 is equal to 114. So if N2 here is equal to 114 rather than 113.1, and the P, we cannot change the P, circular pitch, so we must change the diameter. The diameter is not fixed. We are just trying to find the diameter. So it's 900, but we need to find the exact diameter D2 so that when we multiply it by pi and divide by 25, we are getting 140. The same is here. We need to find the diameter D1 that is multiplied by pi and divided by 25 gives 38. These diameters, the 900 and the 300, they give us these numbers, which we are not using. So if we are using new numbers for the gears, the gear teeth, so we must use new diameters as well to just keep this 25 the same, to keep the ratio, the gear ratio 3. Okay. In this case, we can use this equation, D1 is equal to P multiplied by N1 divided by pi, which is obviously coming from this equation. So this equation we can find the simplify to find the so D1, which is the pitch circle diameter of the first gear, is equal to P, which is 25, multiplied by N1, which is 38, divided by pi. So now we are getting the integer number of teeth for first gear. We make this number fixed because it was given. So in this case, the new diameter is going to be 300.36 millimeters. It's very near, very close to the 300, but this is the exact number that will make sure that the number of teeth is 38 and the circular pitch is 25. So we can repeat this for gear 2, so where D2 is equal to P, which is 25, multiplied by N2, which is 114, divided by pi. So in this case, we are getting 907.08 millimeter for the diameter. Now these are the exact diameters. Based on the exact diameters, we can find the exact center distance. And remember, it was in the problem, it says that C is equal to about 600, approximately 600. So now, based on these diameters, the exact diameters, we say that C is equal to D1, which is 308. 02.36 plus 907.08 divided by 2, and then this gives us 604.72 millimeters. So hence the number of teeth of the first and second gear must be 38 and 114. The pitch circle diameters, D1 and D2, must be 302.36 millimeter and 907.08 millimeter respectively. And the exact center distance for this gearbox is 604.72 millimeters. So our next problem is another gearbox. So the reduction speed ratio of the reverted gear trains. We have a gear train here. It is designed to reduce the speed. So the speed, we have an input shaft here. With this input shaft, we have gear A. Gear A is engaged with gear B. And then gear B and C, they are on the same shaft. They do have the same speed. And then gear C drives gear D, which is attached to the output shaft. So NA here is the speed of the input shaft. ND is the speed of the output shaft. And the center distance between these two stages is given as 200 millimeters. So again, the reduction speed ratio of the reverted gear train as shown in the figure is to be 12. So the reduction gear ratio, it means that the gear ratio or the speed ratio is 12. And keep in mind that this, because we are reducing the speed, so the input shaft here has a higher speed than the output shaft. The module of gears A and B is 3.125 millimeter, and of gears C and D is 2.5 millimeter. So we are given here that the module of these two gears is 3.125, and the module of these two gears is 3.125. Calculate the suitable numbers of teeth for the gears. So we are required to find a number of teeth for gear A, gear B, gear C, gear D, based on the given information. And also, no gear is to have less than 24 teeth. So we need to keep the number of teeth higher than 24 for any one of them. So how we can start to solve this problem? So what is given here, the speed or gear ratio is NA, which is the input shaft, the speed of the input shaft, divided by the ND, which is the speed of the output shaft, is equal to 12. The module MA is equal to the module MB is equal to 3.125 millimeter. The module MC is equal to the module MD is equal to 2.5 millimeter. And small na here is the speed of gear A. Capital Na is the number of teeth of gear A, and small r A is the pitch circle radius of gear A, and so on. So this is similar for the rest of the gears. I mean, they have the same, just change the subscript. So we start again with the train value of a gear train. So it's the same. The train value is the product of the driving tooth number divided by the product of the driven tooth numbers, and then the speed of the last gear, which is ND in this case, is equal to the train value multiplied by the speed of the first gear, which is N sub A in this case. So E here is N last divided by n first, which is nd divided by na. Remember that this ratio is given, but it was given na divided by nd rather than nd divided by na. So in this case, E, which is the train value, is nd divided by na equals 1 divided by 12. So because what was given in the problem or the gear ratio was na divided by nd, which was 12. So I'll just getting the reciprocal number here. So the train value is given as following. So we have two stages. This is the first stage between A and B, the second stage between C and D. So we need to find here for the first stage which gear is the driver, which gear is the driven. So for the first stage, the driver is A, the driven is B. So we have here NA divided by NB. And because this is external engagement, so it has a negative sign here. And then NC and ND. NC is the driver, ND is the driven, so we have NC divided by ND here, and because it's external engagement, so we have negative sign here. Negative multiplied by negative gives positive, and we know that E, the train value, is 1 divided by 12. Keep in mind that the speed of gear B and the speed of gear A, they are the same because they are on the same shaft. So in this case, at this point, we have two options. Either if we wanted to get the exact gear ratio, we must factor this number. We must factor this number, for example, between the stage 1 and stage 2, say that the E, the total E, the E for the gear train is equal to E1 multiplied by E2, or E for the stage 1 multiplied by E for the stage 2. So is equal to 1 divided by 12. So it means that we need to factor this number. We can factor it, for example, to 1 divided by 3 multiplied by 1 divided by 4. And then this means that the E for the first stage is 1 divided by 3, and the E for the second stage is 1 divided by 4. In this case, will be, in the end, we'll get the exact gear ratio, which is 12. If we don't care too much about getting exactly the same, exactly the gear ratio as 12, we can use the second option, which is like lately the E, the gear train, the train value for the first stage is equal to the train value for the second stage is equal to the square root of 1 divided by 12. So we understand from this point that in the end, we will be getting the gear ratio as almost 12. It's not exactly 12. But if you wanted to get it exactly 12, you could say E for stage 1 is equal to 1 over 3. And E for stage 2 is equal to 1 over 4. When you multiply 1 over 3 by 1 over 4, you are getting 1 over 12, which is this number. So you have two options here. If it is mentioned in the problem that you must get the exact number for the gear ratio, so you need to factor this number. Otherwise, you just need to use the square root. So this is your stage 1 in A divided by NP. So the E for stage 1 is NA divided by NB is equal to the square root of 1 divided by 12. And from here, we can get a ratio between NP and NA. So if we simplify this equation, so NB here is equal to 3.464 multiplied by NA. And we consider that the E for stage 2, the train value for stage 2, which is NC divided by ND, which is here, this stage, is equal to the square root of 1 divided by 12. So in this case, if we simplify, we get that ND, the number of teeth on gear D, is equal to 3.464 multiplied by NC, the number of teeth on gear C. So I've got two equations here. Remember that the E for the whole gear train is equal to E for stage 1 multiplied by E for stage 2, because we have two stages here only. But if we have more stages, so we say E is equal to E for stage 1 multiplied by E for stage 2 multiplied by E for stage 3, and so on, depending on the number of stages that you have got in your gear train. The center distance here was given, it's exact, is 200 millimeters. So we say that C, the center distance is dA plus dB divided by 12 if we consider the first stage. So it's the center distance is the distance between this line, this center line to this center line. So it's the radius of this gear plus the radius of this gear, or the diameter of gear A plus the diameter of gear B divided by 2, which is eventually the radius of A plus the radius of B. They are the same here. So the radius of gear D plus the radius of gear D, C and D, or the diameter of gear C plus the diameter of gear D divided by 2. If you get the diameter divided by 2, it's the radius of gear C, and if you get the diameter here divided by 2, it's giving you the radius of gear D. So the definition of the module is that the module is equal to D, which is the diameter, the pitch circle diameter, divided by the number of teeth. So what we need to do here, we just need to get this equation as a function of the number of teeth rather than the diameter, because we have got already two equations as a function of the number of teeth. So we say here the left-hand side C is 200 is equal to the diameter of A. So if you simplify this equation, you will find that the diameter is equal to the module multiplied by the number of teeth. dA here can be replaced by MA multiplied by NA, the module for gear A multiplied by the number of teeth of gear A, plus the module of gear B multiplied by the number of teeth of gear B divided by 2. And the right-hand side here can be replaced by the module for gear C multiplied by the number of teeth of gear C plus the module of gear D multiplied by the number of teeth of gear D divided by 2. So we've been given that the module for gear A and B, they are the same, 3.125. So we can get here the MA and MB, they are the same. We can factor out this M value to be like 3.125. On the right-hand side also, we've got MC and MD, they are the same. We can factor out this M value, which is 2.5. So if we multiply the left and right hand sides by 2, so I've got here 400, we've got here MA, MB, they are the same. We get it as a common factor here, 3.125 NA plus NP. And on this part, we've got MC and MD, they are the same. We factor out this number as 2.5, and then we end up with 2.5 multiplied by NC plus ND. Eventually, these are two equations, not only one equation, because if you take the 400 with the this part in the middle, so this is one equation, and if you take the 400 with this part, so you have another equation. So I have two equations here. The first equation is going to be NA plus NB is equal to 400 divided by this number, which is the module MA or MB, 3.125. If you divide these numbers, you will get 128. This is equation 3. Then for the second equation, NC plus ND is equal to 400 divided by 2.5, which is 160. This is equation number 4. Now we've got 4 equations and 4 unknowns. The 4 unknowns are the number of teeth for the 4 gears, and the 4 equations are known now. So if we substitute the first equation, which was this one, NP is equal to 3.464 NA, we substitute this equation into equation number 3, which is this equation here, or up here. So we say that NA plus NB, so NB in this case is going to be 3.464 NA is equal to 128. So based on this equation, we can get NA. So NA here is 128 divided by this number. Again, so this is, we cannot use the number of teeth as a fraction. So we need to round this up or down. So it's 28. So we can use this as 28. But here, because the center distance is constant, is fixed, so we need to make sure that the number of teeth and consequently the diameter is giving us the exact center distance. So we see here that if we go back to this equation that is coming from the definition of the center distance, so it says in order to keep the center distance as 200, so NA plus NB is equal to 128. So we can here substitute this value, which is NA, substitute it in this equation here to get the value of NB. So NB is equal 128 negative minus 28, which is 100. So if we have the NP as 100, the NA as 28, so this is giving us 128, which very satisfies this equation and consequently satisfies the center distance to be 200. We'll do the same for the equation number 2 and 4. So equation number 2, which is ND, the ratio, the relationship between the number of teeth of the gear D is equal to 3.464 NC. So we substitute this equation into equation number 4, which is this one, NC plus ND is equal to 160. So we replace here ND by 3.464 NC, and we just finish up with this equation, NC plus 3. So it's NC plus 3.464 NC is equal to 160, and consequently the number of teeth on gear C is equal to 35.84. We cannot take this number as it is. We need to round this number up to 36. But again, in order to keep the center distance the same as 200, so we need to use the equation number 4 to find the number of teeth in D. So if we substitute this number in C into equation number 4, so this is going to be 36 plus ND is equal to 160. So consequently, the ND is equal to 160 minus 36, which is 124. So we satisfy now the center distance as to be 200 millimeter for the first and the second stage. So now we need to just get the exact train value based on the number of teeth that we've got. So the exact train value is NA divided by NB multiplied by NC divided by ND. So the NA was found to be 28, the NB is 100, the NC is 36, the ND is 124, which is giving us, if you remember, it was the exact value was 1 divided by 12. So this is giving us 0.0813, and the given train value at the beginning was 1 divided by 12, which is 0.0833. If you compare these two numbers, they are close enough, but they are not exact. They are not exactly the same because we have used the square root. So if you wanted these two numbers to be exactly the same, so you need to use the to factor this number 1 divided by 12. You need to factor it to two numbers multiplied together, like 1/3 multiplied by 1/4, or 1/2 multiplied by 1/6, and so on, in order to get this exactly the same value. So the last problem here is epicyclic gear. So we have an epicyclic gear train is shown in the figure. And you see here we have got the ring gear number D. We have got the sun gear in the middle, number sun A, gear A. We have got two planet gears here, B and C. They are the same. They are exactly the same. They are identical. We have got the arm in here that is carrying these two planet gears. So it says here the sun gear A, if the sun gear A rotates 1 revolution in the clockwise direction, so it means that this one is negative because the clockwise direction is negative. And the ring gear D rotates half revolution in the counterclockwise direction. So the NA and ND are given here. And it says, what is the speed of the arm? Find the speed of the arm if sun gear A rotates 1 revolution in the clockwise direction and gear D rotates half revolution in the counterclockwise direction. This is the first part of the problem. The second part says find again what is the speed of the arm, but in this case if the sun gear rotates 1 revolution in the clockwise direction and the ring gear D is stationary. And the number of teeth for sun gear is 40. The number of teeth for the ring gear is 90. So we're going to solve this problem using the tabular form or the tabular method. But before we use it, we need to investigate the geometry, because we can here, using the geometry, we can find the number of teeth for the planet gear B or C, because they are identical. So if you look at this geometry, you will find that the diameter, if you take the diameter of the sun gear, add to this diameter, the diameter of the planet gear B, and add to this the diameter of the planet gear C. So you'll figure out that these three diameters, they are equal to the diameter of the ring gear D. So diameter A plus diameter B plus diameter C is equal to diameter D. We understand that planet gear B and C, they are identical, so the diameters are the same. So this equation can simplify to dA plus 2 dB is equal to the diameter of the ring gear. And since the number of teeth is proportional to their pitch circle diameters, so we can here replace the pitch circle diameters by the number of teeth. So dA is becomes NA, because here we are using the module. The module here multiplied by n is equal to the diameter, but in the end the module will cancel out, because the module of all the gears are the same. We assume that the module is the same. So in this case, so we will have NA plus 2 NP is equal to ND. NA is given as 40, ND is given as 90, and then based on this equation, we can get the NP or NC. They have the same number of teeth as 25. Coming to the tabular method, so we just build a table first. The first column is called condition, and then the second column we start with the input. So the input here is sun gear, so we call the second column the sun gear, and then the sequence or the order of these columns are optional. So we call this arm, we call this planet gear P or C, and we call the last one gear ring gear D. We have two conditions here. They are fixed for any circle, for any epicyclic gear train. So the first condition is that lock all the elements, lock all the gears to the arm as if you are welding them to the arm, and then give the arm y RPM. So give the arm RPM of a value of y. So it means that if they are welded together and one part rotates with y, so all the parts will rotate with the same speed. So gear, the sun gear has y RPM, the arm has y RPM, the planet gears P or C, they have y RPM, and the ring gear has y RPM. The second condition is that lock the arm and give the sun gear x RPM. So we just hold the arm here. We just hold the arm. We don't allow the arm to rotate. It means that the speed of the arm is 0. So you need to remember this. If you lock the arm, it means that the speed of the arm is 0. Now, if we are given the sun gear a velocity or RPM x value, so how we can find the RPM for the planet gear B and the ring gear D? This is our job now. So in order to find the speed of the planet gear B or C, because they are identical, so you can work on one side only. So we need to remember this equation. So we consider them as one stage. The sun gear rotates as the input or the first gear, and the planet gear rotates as the output or the last gear. So if NA is the speed of sun gear, and NP is the speed of the planet gear, and we consider we have one stage here, one gear stage. So we say that E is equal to N last divided by N first. If we have sun gear A engaged with planet gear B, so we consider that this is the first gear, which is sun gear, is the first gear, and the planet gear is the last gear. So N last is NP divided by N first, which is NA. And the ratio of the speed ratio is inversely proportional to the number of teeth on the gears. So if you remember, we consider that E is equal to the number of teeth of the driver gear. So the driver gear here is sun gear, so that's why it's NA here, divided by the number of teeth on the driven gear, which is NB. So we can use this equation to find the speed of the planet gear. So the speed of the planet gear here, V, based on this equation, NP is equal to NA divided by NP multiplied by NA. So NP here, which is the speed of the planet gear, is equal to NA, the speed of the first gear, which is the sun gear in this case, multiplied by NA divided by NV. And it has a negative sign here because they are externally engaged together. So that's why if we consider that NA is X, as we've assumed here, so NV is equal to negative X multiplied by NA divided by NV, which is the speed of the planet gear here. So we do the same between B and D. So we consider that planet gear P is the driver for the ring gear D. So B is the driver, D is the driven. So we say here that the speed of the last gear, and D in this case, is equal to the speed of the first. The first gear in this case is NB, which was the speed of NB is this much. So we just get the speed of NB, which is negative X multiplied by NA divided by NB. And then this is multiplied by the E value between the planet gear B and the ring gear D. So it's the number of teeth on the driver. So considering that the planet gear is the driver, so it's NP divided by the number of teeth on the driven, which is ND. So NP divided by ND is the train value for this stage between B and D, and this number here, or this value here, is the speed of the first, or the driver gear. The speed of the driver gear is negative X NA divided by NB, coming from this cell here. And NB divided by ND is positive. It's taking positive sign because they are internally engaged together. That's why it's getting here a positive sign. So this cell, the equation in this cell here, gives us the speed of the ring gear D. What we need to do next is to get the total, the summation of all the columns. So for example, the summation of this one is Y plus X. The summation of this column is Y plus 0, gives Y. The summation of these values, Y minus X multiplied by NA divided by NB. And the summation of these two conditions is Y minus X multiplied by NA divided by NB multiplied by NP divided by ND. And you see here that NP can cancel out. But here, this value here is the total speed of ring gear. This value here is the total speed of planet gear, either B or C. Y is the speed of the arm, total speed of the arm. And Y plus X is the total speed of the sun gear. So if you are given, for example, the speed of the sun gear, so you need to equate it to these values. Y plus X is equal to what is given as the speed of the sun gear. Okay. If we wanted to find the speed of the arm, so we find the value Y. The value Y is giving us the speed of the arm. If it says in the problem that the ring gear is fixed, it means that this value here is equal to 0, because the speed of this ring gear is equal to 0, and so on. So the first condition was the sun gear A rotates 1 revolution in the clockwise direction. It means that it's negative. And if I go back here, so the sun gear speed is Y plus X. So the sun gear speed is 1 plus X is equal to negative 1. Why negative? Because it's in the clockwise direction. And 1 because it's given here as 1. And the ring gear D and the ring gear D rotates half revolution, so it's equal to 1/2 in the counterclockwise direction, so it's positive. So if I go back to the table, where is the speed of ring gear D? So this is the speed of ring gear D. So take this one and equate it to 1/2 positive 1. And these are the two equations. If you cancel out the NV, so you simplify and you are getting here y minus x multiplied by NA divided by NV. And you know that NA is given as 40 and ND is given as 90 is equal to 1/2. So we have equation 1 and equation 2, and we have two unknowns, y and x. We need to solve equation 1 with equation 2 to get the x and y values. So after you solve these two equations together, either by direct substitution or using your calculator, you will find that x is equal to negative 1.04 and y is equal to 0.04. If I go back to the table, you will find that y here is the speed of the arm. So in this case, the speed of the arm was required. It's y, so it's 0.04 revolution in the counterclockwise direction. Why? Because it's positive. And you see here, when the sun gear rotates one revolution, just one revolution, 360 degrees, and the ring gear rotates 1/2, so it rotates 180 degrees in the clockwise direction, and the sun gear rotates one revolution 360 degrees in the clockwise direction. So in the end, you will find that the arm here will rotate 0.04 revolution in the counterclockwise direction, the same direction as the ring gear. Okay, and you see here the ratio is too much. I mean, this is 1 and this is 0.04. So in this case, we are just reducing the speed too much. And this is one of the advantages of using the epicyclic gear. So for the second condition, we had here the sun gear rotates one revolution in the clockwise direction, but the ring gear was stationary. Stationary means that the speed is equal to 0. So we repeat again, we take the y plus x is equal to negative 1, which is the speed of the sun gear, and this is our equation number 3, and the speed of the ring gear is equal to 0 because it's fixed, it's stationary. And we just cancel out these two values. So you see here that the planetary gear was like idle. So even the number of teeth for this gear is not required. But sometimes we just ask you first to find the number of teeth for gear B. So in this case, if we simplify, so we get y minus x multiplied by 40 divided by 90 is equal to 0. You have again two equations. They are different because this equation is different now. We have 0 here. When you solve these two equations together, you are getting different values for x and y. And you see here that y in this case is negative 0.308 revolution in the clockwise direction. So it rotates in the same direction as the sun gear now. And the ratio is different as well. So I hope this helped you to capture the main concepts that we were talking about, and thank you.